Okay, so my name is Adil, and I am a PhD student at Uppsala University. And today I'm excited to present my ongoing work, which is track reconstruction using geometric deep learning in the straw tube tracker. And yeah, so here is my short outline. I will start from my motivation and will end up giving you the results. I will quickly skip certain slides as they have already been presented in Anna's talk in much more detail. So let's, what is the motivation? And okay, so at PANDA, the 6 studies involves the QCD in the confinement domain, and where we have the beam energy, which is less than 15 GeV. And then we have many subdomains like nuclear structure, hyperend physics, etc. To explore. And we expect that we have a low PT tracks under 1 GeV, and approximately we might have like 8 tracks per event. In most of the cases, we have the events which have a displaced vertices. For example, hyperons, they decay significantly away from the interaction point, and most of the time they actually decay in the straw tube tracker, skipping the inner tracker detectors. And of course, we need a highly efficient track reconstruction algorithms for such studies. So here is the figure of the fair, which is under construction. And the important thing is that we have a beam energy from 1.5 to 15 GeV. And we are expecting that the interaction rate will reach up to 20 megahertz. And here is the PANDA detector. We have 2 spectrometers, the target and the forward, and I'm focused on the straw tube tracker, which is in the target spectrometer. And let's look a bit deeper into what the STT is. And you have already seen what that STT looks like in this in the previous slide, in the previous talk by Anna. So the important information you can get from here is that we need for a particle to reach the innermost layer is it needs 50 MeV momentum, and to reach the outermost layer, the minimum PT is 100 MeV. Okay, so what is challenging for us now is that to construct tracks in STT is that the first is the geometry itself. It is hexagonal, and it has arranged straw tubes in 6 different sectors. And because these are gas tubes, so we also have these isochrones in it. So we are not very much sure where the particle hits. So we need some kind of procedures to include the isochrone radii into the hit position. And the tracks which we expect they are spiraling, overlapping, and crossing tracks. So we have a sparse data, but our tracks are complex. And so we're thinking, can we address these issues with the graph neural nets, for example? So for that, I have a deep learning pipeline. So the data for this pipeline is simulated using the PANDA root. And this data set is then converted into the layer-wise input graphs. I use interaction graph neural nets as a learning model, and I use extra track pipeline as a baseline. So I build my code on top of that. And finally, track labeling and the evaluation of reconstructed tracks. So let's look into the data set. So I use, because it's a new work, so I start from taking 5 muon pairs per event using a double box generator, which is a wrapper over particle gun. Energy range I chose is 100 MeV to 1.5 GeV. And to simplify my track reconstruction, I skip the skewed layers from my data, and also the hit positions are taken as the position of the anode wire. And at the start, I ignore the isochrone radii. And track reconstruction is in XY projection of the STT. So the total 100,000 events split it into 95 and 5% of the data. So the graph construction is done like this. So I start from the inner layer to the outer and repeat it until I reach the last layer. I restrict my graph construction into adjacent sectors. For example, you cannot, I do not allow a track to be reconstructed in, like, for example, from this track to there. So it should be in the adjacent sector as well. And my input graphs includes true edges and false edges. And of course, my true graph contains true edges. So here is a schematic of interaction graph neural net. You have heard a lot about it, so I will quickly skip it. After I run my whole pipeline on my data, I have my performance evaluation of my network using a ROC curve, which is an efficiency versus purity. And my area under the curve is above 0.999. So it means that my neural net has trained very well on my training data. Okay, so after that, so the next task is to label these predicted edges into convert them into track candidates. So what we get from the neural net is a weighted graph. So we have hit pairs and we have associated edge score. So we apply a DB scan algorithm with a certain cut to build track candidates out of it. So I have scanned through different epsilon parameters and it chose epsilon equal to 0.25, which is chosen because of high efficiency with low fake rate. Okay, so once we have track candidates, we try to evaluate them, that how good track are constructed. My reconstruction efficiency on my test data set is roughly 95%, and with a fake rate of 0.4, but I do have a high duplication rate, which is around 16.63%. So to investigate further, we have divided our data set into two subsets into clean and complex events. So the clean are the ones where tracks are not overlapping. So, and the complex includes everything overlapping and crossing tracks. So for the clean data set, I can, my efficiency was increased to 98%. My fake rate is reduced to half, and my duplication rate also significantly reduced. But for the complex category, it is difficult to define like how the complexity of the events. So you can, for example, have a couple of tracks in an event which are overlapping, and you can also have more tracks in an event which are overlapping. So it is difficult, but overall we have an efficiency which is relatively lower than our clean sample. So in the complex event, you can expect some events like this. So here, what our algorithm failed to reconstruct very well. So for example, you have, in this event, you have a one track, which is not only crossing another track, but it's also curling inside. So as I said, I create input graphs by layer-wise from first layer to the next. So it has a difficulty when a track is curling back. So this is not, we are looking into how to tackle such events. And on the right, you see how it was reconstructed. So 75% efficiency with a high fake rate and duplication rate. So probably one track, two tracks are merged together. Okay, so the conclusions are that if we have a quite clean sample, then our efficiency goes approaches 98%. And but if we do have a complex category where we have all the kind of events which I showed you, then my duplication rate increases and also efficiency drops significantly. So far, to tackle duplication tracks, we are thinking about to adopt a different approach. And one such approach is like a Wrangler algorithm from also extra track, and I am intending to explore that. So finally, the outlook is that I would like to minimize the duplication rate. So I want to tackle those events where tracks cross each other or share a certain segment of each other. And I said I am using only the anode wire as a hit position. So in reality, we need to accommodate, incorporate isochrone radii. I would like to do a hit correction on it. And I skipped the skewed layers. I want to put skewed layers back to see how they affect my tracking algorithm. And also one can extend it to MVD and GEM detectors, which closer to the interaction point. And then once everything is under control, I would like to use some realistic studies, for example, the Hyperon reconstruction. So the PP bar to lambda bar to proton and pions. And I am end of my talk. And thank you for listening.
Questions? There is a strange drone sound in the background, but questions?
Question is a question, I think.
Maybe that is a question. No? Questions on Zoom? You have a question.
Yeah, so this is Daniel. Thanks, this is really, really good performance. I'm curious, what's the sort of standard, does PANDA have a benchmark algorithm that they're planning to use? And do you know the performance of that algorithm, that reconstruction algorithm?
So at PANDA, we have an ideal track finder, which can be used for primary tracks. So that is uses like Monte Carlo information to reconstruct tracks. So that algorithm gives you like an upper limit how and any other realistic tracker can reach. But for we can use that as a benchmark, but I don't have a study like, for example, is which I can directly compare to my data, like muon pairs, for example. So usually these studies are done when we are developing something, so they are quite local to the person who is doing it. So I have not benchmarked it with the ideal track finder. But one can use that one to directly compare these two with this data set.
Anybody else?
So there's a question from Danton who cannot, when he speaks up, you can't hear him. The question is, do you use DB scan to cluster hits or edges?
So the DB scan we use is, so we provide them connected components to DB scan, and the DB scan runs over it. So it's collect hits which have higher score.
Thanks, Andy. And I had missed it. I don't see any more hands, so let's thank Adil again.